Okay, so recall the setup. It's inter-arrival times, which are x1, x2, etc., IID exponential alpha. And the arrival times, the 0th arrival time is 0, and nth arrival time is just the sum of first n inter-arrival times, x1 to xn. Now here is the first question. It's more like a warm-up question. Suppose you fix a t positive. The question is, what is the probability that no call arrives up to time t? This is a very easy question that can be answered in this setup. So this probability, the probability that no call arrives up to time t, is same as saying that the first call arrives after time t. If you have no call after time t, it's same as saying that the first phone call arrives after time t. This is same as saying first arrival time, remember, is S1. Sn is the nth arrival time, so first arrival time is S1. So you're asking the probability that S1 is bigger than t. Now, S1 is same as X1 and it has an exponential distribution. So therefore, we're just asking the survival function of an exponential distribution, which is this integral. And we know that this is equal to e power minus alpha. So therefore, for every fixed t positive, the probability that no call arrives up to time t is given by e power minus alpha t. Now we'll ask another question in the same setup. We fix again t and say, ask the question, what is the probability that exactly one phone call arrives up to time t? Now this probability, namely the probability of exactly one phone call arriving up to time t, is same as saying the first call arrives, okay, whenever I say up to time t, I mean on or before time. Okay? Time t is also included. It doesn't matter because all these random variables are continuous. You can just say it arrives before time t as well, but for convention purpose, it's good to fix whether we want to include t or not. Let's include t. So whenever we say up to time t, we always mean on or before time t. So that means if exactly one call arrives up to time t, same as saying that the first phone call arrives on or before time t, but the second phone call definitely arrives strictly after time t. Because if not, then you'll have two phone calls coming before time t. So therefore, this event can happen if and only if this event, namely exactly one phone call arriving after time t, can happen if and only if the first call arrives on or before time t, but the second phone call arrives after time, strictly after time. So this is same as saying S1 is less than equal to t, which is in turn strictly less than S2. Now recall that S1 is exactly same as X1, whereas S2 is just S1 plus X2. Okay, S2 is X1 plus X2, but then again X1 is equal to S1, so therefore S2 is S1 plus X2. That's what I've written here. Now the next step is to just write it, the same thing slightly differently. Namely, S1 is less than equal to t, but instead of writing S2 is bigger than t, I'll write X2 is bigger than t minus S1. Now, why do I do that? Why do I write the same thing differently? The reason is that now I'm going to condition on S1. Okay? I'll fix S1 and try to compute this probability, and then I'll integrate over all possible values of S1, which is going to be from 0 to t. Okay. So this is the next step. So we condition on S1, taking a value very close to u, which we always denote by S1 equal to u, but we always mean S1 takes a value very close to u. So when S1 takes a value very close to U, then this X2 is bigger than T minus S1. It's just same as X2 is bigger than T minus U, but we have to compute the conditional probability. Since we are dealing with the conditional probability, we have to uncondition it by multiplying with the marginal of S1. And then we have to integrate only from 0 to T because S1 is less than or equal to T. That's the idea of this integral. Okay? We fix S1 at being very close to U. Conditional on that, we calculate this probability of X2 bigger than T minus S1, but now it's becoming X2 bigger than T minus U because S1 is very close to U. But we have, this is the conditional probability. We have to multiply with the marginal of S1 and integrate on the interval 0 to T. So this can be thought of as a continuous analog of law of total probability. Okay. Of course, this has to be justified. I'm going to do that in the next slide, but let's assume that this is true. Okay. We have put 3 question marks here, but let's assume that this is true. Intuitively, this is true, obviously, as I have justified. But once you see that, the rest of the calculation becomes very easy. Why? That's because of the independence in the system. Note that S1 is an exponential random variable with parameter alpha, and it is independent of X2. Therefore, this conditional probability here is actually the unconditional probability that X2 exceeds T minus U. On the other hand, S1 follows exponential, so I can just as well write the density of exponential here. Everything is happening on the positive side of the line, I can just write the density of S1. Also, X2 follows exponential. So therefore, the survival function of X2 is going to be e power minus alpha into T minus U. Okay, we already have computed the survival function of exponential once. So therefore, we can just put e power alpha T minus U. And note that since U is less than T, U is going to be 0 to T, T minus U is something positive. So therefore, this survival function form is valid. Now, the rest is just computing the integration. And we see that once you multiply this with that, U actually gets cancelled. You just get e power minus alpha T. And this you have to integrate that from 0 to T. There is no U in it, so you'll just get a T. You'll just get alpha T times e power minus alpha T. So this is the answer to this question. Of course, subject to justifying this thing rigorously, this particular step rigorously, which we have justified intuitively, namely by saying this is a continuous analog of law of total probability, but it's important that we justify this step once at least. So let's justify this step. So we have to justify, namely, this particular step. We have to start from this and show that this is equal to that. So let's start from this first thing, which is probability of S1 less than or equal to T and X2 is bigger than T minus S1. Now this is same as saying the pair S1 comma X2 is in the set A, where A is the set of all Ux in R2 such that U is strictly bigger than 0 and less than or equal to T. That's because S1 is less than or equal to T. Okay? And S1 is always strictly positive, so therefore that's automatic here. And X2 has to be bigger than T minus S1, which can be ensured by saying X is bigger than T minus U in the set. Okay? If you define A to be this particular set, then the random vector S1, X2 belonging to this set A is same as saying S1 is less than or equal to T and X2 is bigger than T minus S1. Now we know whenever you try to compute the probability of a random vector belonging to a particular set, all you have to do, you have to integrate the joint density on that set. Okay, so you just integrate the joint density of S1 and X2 on set A. Now, integrating on A is same as integrating like this. So if you look at the joint density, you integrate On u, you integrate from 0 to t. That is what is said here. And for every fixed u, you integrate x from t minus u to infinity. That's what the second thing says here. Okay? So integrating on s, this double integral can be written as a repeated integral like this. Now, use the fact that the joint density can be written as the conditional density of x2 given S1 times the marginal density of S1. And this can always be done. Now let's take the integral with respect to s inside. Note that this has no x in it. This is just a marginal density of S1. So the variable there is u. So therefore that can go outside. So let's compute this integral first. Everything is non-negative, so we can compute any integral first, and that will give me the joint integral. So therefore, let's compute this integral first. And that's essentially you're integrating the conditional density of x2 given S1 equal to u. S1 is very close to u, that is, on the interval t minus u to infinity. So this will of course give you the conditional probability. So the inner integral, which is in bracket, will give you the conditional probability of x2 bigger than t minus u, given that S1 is very close to u. And of course, outside you have the unconditional probability. So this is exactly what we had to prove. Okay, so this justifies that step, namely that that we put 3 question marks on. So from now on, we are not going to justify this kind of steps. We'll just assume it as a continuous analog of law of total probability. And we'll always say that such a probability is equal to conditioning on S1 equal to u. This is this probability, and then we have to multiply by the marginal and integrate that probability. So from now on, we're not going to justify. But all of them that we are not going to justify can be justified in a manner parallel to this one. Okay, with that said, let's try to generalize the previous question. So recall that we have the inter-arrival times xi's, which are IID exponential alpha. We define S0 to be 0, and mth arrival time Sm is the sum of x1 up to xm for each positive integer m. Okay, so now fix 2 things. Fix t positive, a real number t strictly positive, and a positive integer n. And ask yourself the following question. What is the chance that exactly n calls arrive up to time t? Earlier we answered the question when n equal to 0, n was equal to 0. What is the probability that no call arrive up to time t? No call arrives up to time t. And also, we answered the question for n equal to 1, namely, what is the chance that exactly 1 call arrives up to time t? Now I'm going to ask the general question. By fixing a positive integer n, what is the probability that exactly n calls arrive up to time t? Now this probability is essentially, by the previous calculation, it should be clear, that the nth phone call happen on or before time t, but the n plus 1 comes strictly after time t. Okay. So exactly n phone calls arriving up to time t happens if and only if the nth phone call arrives on or before time t, and the n plus 1th one arrives strictly after time t. So this is just like before. So these 2 events are the same. So their probabilities are the same as well. In other words, in our notation, we are asking the probability of Sn less than or equal to t, which in turn is strictly less than Sn plus 1. Now note that Sn plus 1 is just Sn plus Xn plus 1 because of this equation here. Okay. So we are going to follow the exact same kind of steps. So we'll write it like this. We'll say this is the same as the probability of Sn less than or equal to t, and xn plus 1 is bigger than t minus Sn. Now, as expected, just like last time, you're going to condition on Sn taking a value very close to u and run u from 0 to t. Okay? So, condition on S1 taking a value very close to u, and then this probability, this thing becomes xn plus 1 bigger than t minus u because Sn is very close to u. So, you have to compute this conditional probability. But since this probability is an unconditional one, we have to multiply by the marginal density of Sn and to integrate from 0 to t over u. Okay, so this is justified. This can be justified very similar to the previous justification. So from now on, we are not going to justify such things. We're just going to say this is a continuous version of law of total probability, and then we use the fact that Sn is just sum of x1 to xn. All the xi's are independent, and xn plus 1 has nothing to do with x1, x2 up to xn. Okay? Since all the xi's are independent, and Sn is just the sum of first n of them, the n plus 1 at 1, namely xn plus 1, is going to be independent of Sn. Okay? So therefore, this conditional probability can be changed to an unconditional probability of xn bigger than t minus u. Okay? So this is because of the independence of Sn and xn plus 1. And that happens because all the xi's are independent, and Sn is a function of the first n of them, whereas xn plus 1 is the n plus 1 of them. So that makes them independent. Now let's put the values in. We know that xn plus 1 follows exponential distribution, parameter alpha. So therefore, the survival function is of this form. Note that t minus u in this range, t minus u is going to be positive. So therefore, we'll have this integral in this value of this survival function. On the other hand, Sn follows gamma n comma alpha, gamma with shape parameter n and scale parameter alpha. So therefore, you just put the value of that here. Okay. So now you have to see what gets cancelled and so on. You will see that this integral is actually just integrating this part. That's because this multiplied by this would become e power minus alpha t, and this integral is over u, so that will come outside. Okay, so e power minus alpha t will come outside. This times this is e power minus alpha t, which will come outside, and so will the other constants like alpha power n divided by n minus 1 factorial. Okay, so everything comes outside. There's nothing to this. This is just a constant in this integral. There's no u in it. The only integral will be from 0 to t of u powered n minus 1 du. And that's just, this integral is just u power n divided by n. So that will give us u powered n will come inside this. So this is u power n, but we are integrating from 0 to t. So this integral is actually t power n by n. Sorry, yeah, it's t power n by n. So that will be absorbed here. So that makes it alpha t power n. And n in the denominator gets multiplied with this n minus factorial to give you n factorial. So this is the form of the probability of exactly n calls arrive up to time t, namely on or before time t. Okay, so let's summarize the whole thing, what we have obtained so far. So in our setup, if you fix t positive and a positive integer n, the probability of exactly n calls arriving up to time t is given by this equation. You give it by this thing. It's e power minus alpha t into alpha t power n by n factor. Now note that we had taken n to be a strictly positive integer, but it also holds for n equal to 0. That's because we had calculated, as our verb question, the probability of exactly 0 call arrive up to time t is e power minus alpha t, which is just same as this value if you put n equal to 0. Okay? So therefore, this equation 1, is actually valid for all t positives, for all real number t, strictly positive, and for all integers n bigger than or equal to c. Okay? Okay, so this summary is going to be very useful for us